What's up, team? Quick question before we start. Do you actually know mlflow 3 evaluation, scorers, judges, tracing, and the RAG Eval Triad? By the end of this video, you will. Let's dive in. Your chatbot gave a wrong answer. Was it the retriever's fault or the generator's? Without the right evaluation setup, you can't tell, and a Fortune 500 client just put that exact question in writing. By the end of this video, you'll know how to give that client 2 specific numbers from mlflow that prove which half of your RAG system is to blame. Quick context: Episode 10 measured the retriever in isolation with precision at K, recall at K, NDCG, and MRR. Episode 12 wrapped the chatbot in PyFunk and shipped it on model serving. But none of that proves the system works to someone writing a check, and that's today. 5 terms will anchor everything that follows. mlflow.genai.evaluate is the harness, one function call that runs your app over a dataset. A scorer is the unit of evaluation logic. It produces 1 score per row. An LLM-Judge is a scorer powered by a language model. It reads the answer and gives a verdict with reasoning. Expectations is the dataset field that holds ground truth, like an expected response or expected facts. And the RAG Eval Triad is the 3 diagnostic questions that pinpoint where a bad answer came from. Here's the scenario in full. DataDino just landed a Fortune 500 natural history client for the museum chatbot. The contract has accuracy thresholds written into it, real numbers the chatbot has to clear. On the kickoff call, procurement asks how DataDino measures accuracy. The engineer says, "We compute cosine similarity between the chatbot's answer and a reference answer." Procurement asks one follow-up, and the whole story collapses. The rest of this video is what that engineer should have said instead. Here's why that follow-up landed so hard. On the left, the reference says Paris is the capital of France, and the answer says Paris is not the capital of France. One word, not, completely flips the meaning. But if you're computing cosine similarity on raw word counts or TF-IDF vectors, the score barely moves, because almost every token overlaps. On the right, the reference is the same, but the answer says London is the capital of France. One word changed, catastrophically wrong, and yet because almost every other word matches, cosine similarity calls that pair close. The metric rewards confident hallucinations and hides contradictions. It's measuring word overlap, not truth. So pin this one down before we go any further. Vector similarity on the final answer measures word overlap. It does not measure whether the answer is true, whether it was grounded in your documents, or whether it addressed the user's actual question. Cosine similarity is a fine retrieval tool. It is not an evaluation strategy. The official exam guidance puts it plainly: curate a dataset that can test retrieval and generation separately, and use mlflow's built-in evaluation metrics to perform the evaluation on each component. 2 ideas hide in that one sentence. First, you curate the dataset. Somebody writes representative questions and decides what a correct answer looks like. Second, retrieval and generation are scored separately, because they fail for different reasons and need different fixes. The API itself takes 3 arguments. Data is your evaluation set. Each row carries inputs, optional pre-computed outputs, and optional expectations, which is where ground truth lives. Predict_fn is the optional callable that runs your app over each row of inputs. If you skip it, mlflow scores the outputs that are already in the dataset. Scorers is the list of judges and functions that produce a score per row. The output of the call is a run logged to an mlflow experiment, with a comparison view in the UI so you can diff runs against each other. Here's the smallest useful call. Import a few built-in scorers from the mlflow.genai scorers module, hand evaluate a dataset, hand it the chatbot function to run, and pass a list of scorers, correctness, RelevanceToQuery, and safety. That's it. mlflow loops over each row, runs your chatbot, and applies each scorer to the input, output, and expectations. The whole loop is one call. One row of the dataset has 3 slots. Inputs is the dictionary your app is called with. For DataDino, that's the visitor's question. Outputs is optional. If it's there, mlflow uses the pre-computed response and skips calling the predict function. Expectations is the ground truth slot. Expected_response holds a reference answer string, and expected_facts holds a list of facts that should appear. The orange block at the bottom is the important one to remember. Only judges that need labels read it. Everything else ignores it. One small detail worth pinning down. The keys inside inputs must match the parameter names of predict_fn. If your dataset uses the key question but your chatbot function takes a parameter called query, the call fails at runtime. mlflow is essentially calling predict_fn with double-star inputs, so the names line up or they don't. The built-in judges split into 2 buckets. On the left, response quality judges grade the answer itself, things like correctness, RelevanceToQuery, safety, and guidelines. On the right, the RAG bucket grades the retrieval step, RetrievalGroundedness, RetrievalRelevance, and RetrievalSufficiency. Take a moment to scan the layout. The color is the single most important thing on this slide, and we'll unpack what it means next. If you remember nothing else from this video, remember this. Only 2 built-in judges require ground truth, correctness, and retrieval sufficiency. Every other built-in, safety, RelevanceToQuery, RetrievalGroundedness, RetrievalRelevance, and guidelines, runs unsupervised. That means you can point the unsupervised ones at production traffic that has no labels, while the labeled judges only run where you've paid the human cost to write expected answers. Think of it as 2 kinds of teacher. The teacher on the left has the answer key in hand. Correctness and retrieval sufficiency both reach into the expectations field for the labels and grade against the truth. The teacher on the right has no answer key, but is still useful. They can spot a rude essay, an off-topic answer, a claim the source material doesn't support, or the wrong book pulled off the shelf, all without ever seeing the reference. Both teachers earn their keep. They just have different costs. One quick setup before the next section. The retrieval judges grade what the retriever returned, but they don't inspect your code. They read a trace. If tracing isn't wired up correctly, those judges silently return nothing. That's the failure mode most teams hit on their first run. So tracing is next. 3 scenarios that together localize any RAG failure. At the top, context relevance. Did retrieval find the right documents? That's mlflow's RetrievalRelevance. Bottom left, faithfulness. Did the generator actually stick to the retrieved context, or did it make something up? That's RetrievalGroundedness. Bottom right, answer relevance. Did the final answer address the user's actual question? That's RelevanceToQuery. All 3 run unsupervised, which means you can point the triad at production traffic without writing a single label. When you do have labels, you layer correctness and retrieval sufficiency on top. Picture grading an open book essay. Context relevance asks, did the student open the right book? Faithfulness asks, did they actually quote the book, or did they make stuff up? Answer relevance asks, did they answer the question on the test, or write about something completely different? 3 failure modes, 3 different fixes. Bad retrieval means re-rank or re-chunk. Bad faithfulness means prompt the generator harder or constrain it. Bad answer relevance means the system prompt is drifting. The triad tells you which one broke. Before retrieval judges can do their job, they need a trace. Think of a trace as the receipt from a multi-stop ride. It shows every leg of the journey. Spans are the individual legs. Each span has a type, and the canonical type for retrieval calls is spanType.retriever, and that's written in all capitals in code. RetrievalR. The output of a retriever span has a specific contract. It has to be a list of documents, where each document has a page_content field and optional metadata. That contract is what lets the retrieval judges find the docs and grade them. Here's what a traced RAG call actually looks like. At the root, the agent span wraps the whole call to predict. Underneath it, a retriever span captures the vector search call and outputs the list of documents. Then an LLM span captures the prompt plus context call to the language model and its answer. And if the agent uses a tool, like DataDino's check license function from episode 4, that's a tool span. When you call RetrievalGroundedness or RetrievalRelevance, mlflow walks this tree, finds the span tagged retriever, pulls out its document list, and feeds that into the judge. No retriever span, no judgment. The Databricks docs are blunt about this. Retrieval scorers will not work with static pandas data frames that only contain inputs, outputs, and expectations. They need spans tagged as retrieval spans inside an mlflow trace. The practical consequence: if your dataset is ACSV with question and answer columns and your chatbot isn't traced, RetrievalGroundedness silently fails to evaluate those rows. You don't get an error, you get gaps, so instrument your retriever before you reach for the retrieval judges. When the built-ins don't cover your case, you write a custom scorer with the @scorer decorator. The first example here is a plain exact match check. It takes outputs and expectations and returns true when they match. The second example is a trace-based scorer. It pulls the trace, calls search_spans with span type.retriever to grab just the retrieval steps, and checks that at least 3 documents came back. That second pattern, search_spans on the trace, is the workhorse for any custom logic that needs to inspect intermediate steps rather than just the final answer. The contract is small and clean. An @scorer function takes any subset of 4 keyword-only arguments: inputs, outputs, expectations, and trace. You declare the ones you need and ignore the rest. The return value can be a Boolean for pass-fail checks, a number for graded scores, a string for categorical labels, or a feedback object when you want to attach a rationale alongside the score. Read this quote carefully, because it changes how you design production monitoring. In open-source mlflow, custom code-based scorers, both the @scorer decorator and the scorer class, work with mlflow.genai.evaluate for offline evaluation. They are not supported for automatic evaluation, meaning production monitoring, which only supports LLM judges like the built-ins, make_judge, and guidelines. On Databricks, the managed platform may extend this support. Check the current Databricks documentation for the production monitoring scorer compatibility matrix. The safe engineering rule is this: if you write a scorer subclass and try to schedule it against production traffic, it won't run. For production monitoring, reach for @scorer functions or LLM judges instead. Here's the offline versus production picture side by side. Offline, inside genai.evaluate, anything goes, built-in judges, @scorer functions, scorer subclasses, make_judge, guidelines. For scheduled production monitoring, the menu is strictly smaller, built-in judges, @scorer functions, make_judge, and guidelines. The one thing missing on the right is scorer subclasses. Picture it like a kitchen appliance that only works plugged in at home. Great for prep at the counter, but you can't bolt it onto the food truck. So cosine similarity is out. What's the actual spectrum of options? On the left, heuristic metrics like rouge, blur, and exact match measure token or n-gram overlap. They're cheap, deterministic, and perfect for catching regression on summarization or translation. But they're blind to paraphrase, and they're blind to hallucination. They're a spell checker. On the right, LLM judges read the answer and grade meaning with a rationale. They can reach 70 to 90% agreement with human raters depending on the task and the judge model, and they catch the failures heuristics miss. They're an editor. Both have a place. Pick by the question you're asking. Surface regression, use a heuristic. Semantic quality, use a judge. Here's DataDino's full suite, ready to ship to the natural history client. The dataset has inputs and expected underscore facts for every row. The predict underscore FN is the fossil chatbot, already a traced responses agent from episode 11, so the retriever spans are there. The scorers list covers the entire triad: RetrievalRelevance for context, RetrievalGroundedness for faithfulness, RelevanceToQuery for answer alignment. Then Correctness and RetrievalSufficiency take advantage of the expected underscore facts, the team labeled, and Safety covers the contractual safety baseline. 1 call, 6 scorers, every angle covered. And here's roughly what the run prints: 120 examples, 6 scorers. Notice the diagnostic story the numbers tell. Retrieval groundedness sits at 94%, so the model is staying faithful to retrieved context. Retrieval relevance is 89%, but retrieval sufficiency is 76%. The retriever is grabbing relevant docs, but not always enough of them to fully answer. Correctness lands at 81%, which is consistent with that gap. The fix isn't a smarter generator, it's better recall in retrieval. That's the triad earning its keep. Quick API note: because older code samples still circulate, the old generic harness was mlflow.genai.evaluate, with a model argument, extra underscore metrics, and request and response columns. The new GenA-specific harness is mlflow.genai.evaluate, with predict underscore FN, scorers, and inputs and outputs columns, and the ground truth fields that used to sit at the top level, expected underscore response, expected underscore facts, now live nested under a single expectations field. If you see the old names in a snippet, that's the old API, and the migration path is just the rename. Picture this as a tree, and walk it with me. The root question is always the same. Do you have labeled ground truth for this dataset? Take the labeled branch first. From there, 2 leaves. Correctness if you're asking whether the answer is factually right. Retrieval sufficiency if you're asking whether retrieval found enough material. Now back to the root, down the unlabeled branch. 3 leaves. Retrieval groundedness for hallucination. Retrieval relevance for off-topic documents. RelevanceToQuery for whether the answer actually addresses the question. And 1 branch sits off to the side. When none of the built-ins match the rule you need, you write the rule in plain English and hand it to guidelines or make underscore judge. 1 scenario at the top, and every judge has a home. 3 failure modes worth calling out, because 2 of them are non-obvious. First, circular grading. If your judge model is the same checkpoint as your chatbot, you've handed a student their own paper to grade. The bias is real, and it always favors the chatbot. Second, tuning prompts on the metrics you report. That's the same as a student getting last year's exam as practice, then taking this year's exam and being surprised they aced it. Keep a held-out Eval set the model never sees during iteration. And third, the one that breaks client conversations, reporting a single aggregate quality score. Split retrieval from generation, every time, so when a number drops you can point at which half moved. 5 things to take with you. The API is mlflow.genai.evaluate, with data, predict function, and scorers. Ground truth lives under expectations, and only correctness and retrieval sufficiency reach for it. Retrieval judges need a trace with a span type. Retriever span. Class-based scorer subclasses are offline only. For production monitoring you stick to at scorer functions, make underscore judge, guidelines, and built-in judges, and evaluate retrieval and generation separately. Here's why that last one matters. When a client asks why your chatbot gave a wrong answer, you now have a 2-number answer. RetrievalRelevance tells you if the retriever missed, groundedness tells you if the generator invented. That's the whole game. Now let's lock it in with a quick 5-question quiz. Alright, time to put your knowledge to the test. Question 1. A team is evaluating a RAG chatbot with mlflow.genai.evaluate on a curated dataset that has only inputs and outputs columns, no traces are produced by the chatbot. They include retrieval groundedness, relevance to query, and safety in their scorers list. Which scorer will fail to produce meaningful results? Is it A, relevance to query, because it needs ground truth in expectations? B, safety, because it requires the AI gateway to be enabled? C, retrieval groundedness, because it requires a trace with a retriever span? Or D, all three, because mlflow.genai.evaluate always requires expectations? Take a moment to think about it. The answer is C. Retrieval groundedness is a retrieval scorer. It walks the trace looking for a retriever span and pulls out the documents from there. No trace means no documents to grade, so it silently produces no result. Relevance to query and safety only look at the final answer, so they're fine without tracing. Question 2. Which two built-in mlflow judges require ground truth in the expectations field of the dataset? Is it A, correctness and retrieval sufficiency, B, safety and relevance to query, C, retrieval groundedness and retrieval relevance, or D, guidelines and retrieval relevance? Take a moment. The answer is A. Correctness grades the answer against expected response or expected facts, and retrieval sufficiency checks whether retrieval pulled in the expected facts needed to fully answer. Every other built-in judge runs unsupervised. Safety, relevance to query, retrieval groundedness, retrieval relevance, and guidelines all work without labels. Question 3. A platform team wants to set up scheduled production monitoring on a deployed agent. They have written a custom evaluator as a subclass of mlflow.genai.scorers.scorer with stateful instance attributes. Why will this not work as scheduled production monitoring? A. Scorer subclasses cannot be serialized for distributed execution. B. Production monitoring requires every scorer to return a feedback object, which scorer subclasses cannot produce. C. Stateful scorers require lakebase, which is incompatible with a monitoring service. Or D. Class-based scorer subclasses are only supported in offline mlflow.genai.evaluate. Production monitoring only supports built-in judges, make judge, guidelines, and at scorer decorated functions. Take a moment. The answer is D. The official mlflow docs are explicit on this. Class-based scorer subclasses work fine inside offline evaluate calls, but production monitoring's menu is strictly smaller. It only accepts built-in judges, make judge outputs, guidelines, and at scorer decorated functions. The fix is to refactor the class into an @scorer function or use a built-in judge instead. Question 4. Your team adds retrieval relevance and retrieval groundedness to an mlflow Eval run on a RAG chatbot. Both scorers come back with empty scores on every row. No errors, just blank. The generation side scorers like relevance to query worked fine. What is the most likely cause? A. The expectations field is missing from the dataset. B. The app's retriever span is not tagged with span type.retriever, so the scorers can't find the retrieved documents in the trace. C. The judge model rate limited and silently dropped the rows. Or D. mlflow.genai.evaluate requires predict_fn to return a list, not a string. Take a moment. The answer is B. Retrieval side scorers don't inspect your code. They read the trace your app emits, and they locate retrieved documents by looking for a span-tagged span-type.retriever with the right output schema. If that tag is missing, the scorers have nothing to grade and silently return blank. No error, just empty rows. Expectations would only matter for ground truth judges like correctness, not for the unsupervised retrieval triad. The tracing contract is the part most teams miss on the first run. Question 5. A DataDino client reports a wrong answer from the museum chatbot, and you want to localize the failure in under 5 minutes. Which two judges, run together, let you decide whether the retriever or the generator is to blame? without requiring labeled ground truth? A. Correctness and retrieval sufficiency. B. Retrieval relevance and retrieval groundedness. C. Safety and guidelines. Or D. Relevance to query and correctness. Take a moment. The answer is B. Retrieval relevance and retrieval groundedness. This is the diagnostic pair from the RAG-Eval triad that runs unsupervised. Retrieval relevance asks whether the retriever fetched on-topic documents that tells you if the retriever missed. Retrieval groundedness asks whether the answer is actually supported by those documents that tells you if the generator invented something. 2 numbers, 2 diagnoses, no labels required. The other options all include at least one judge that needs expectations populated, which doesn't fit the no ground truth constraint in the question. That wraps up mlflow 3 evaluation, scorers, judges, tracing, and the RAG-Eval triad. The Databricks Gen AI Engineer Cert has more videos coming on the trickier topics. Subscribe so the algorithm tells you when. Thanks for watching.